Hello everyone, hello people. This is another dose of Drew. I am said Andrew. I am doing another bit on my continuing war with the Collatz conjecture, and that I'm coming at it at a way that I haven't ever seen before. So I'm putting it to video. And what I'm coming at is if we're going to build a function that gets all the powers of 2 from odd positive integers, right? We know what happens if it's even. You divide by 2, and that'll get you either down to an odd, or it'll get you to 0 or 1, or whatever it is, so you know you have a power 2. The other thing is, so we need to know what happened when it's odd, and there's 2 ways you can make odd. I'll use k for this one for a variety of reasons, but 2k plus 1 and 2k minus 1, right? And I'm going to split them up into the positive way to find them and the negative way to find them. We're going to stick with the positive direction because we're going to have the domain of k be all natural numbers, which means its range will be 1, and I shouldn't put 2. It should be like 1, 3, oops, so on and so forth. Hey, it is what it is. I was writing fast if you can't tell. Right? And so we'll come to n. The domain of n is the range of k, and the domain of x is going to be the same as k. And n is defined for the range of k as 2k plus 1, right? So n is odds. I'm going to go with the coprime thing of the 6k plus, you can do it right at plus or minus. I'm going to split it into the positive and negative parts, right? So all positive integers are of a form this, right? 6k plus 0, 1, 2, 3, 4, 5. Right, so it's some multiple of 6 or some number in between the multiples of 6. And I'm going to use that as the basis. First of all, a lot of people probably already know the 6k plus and minus 1, which the negatives can do, but we'll do it for the positives, which is the 6k plus 1 and plus 5. All the primes are going to lie within that. So if we're trying to find something to do with odd that will get to a power 2, we don't want those. Right? Another thing is going down the list here, we can look at the 6k plus 3 one, which is going to be odds, but they're going to be odd numbers without any primes. All the primes are going to be up here, so by default, any one of this form is going to be an odd number, but it won't have any primes in it. Right? So that's okay. We kind of like that. We like odd numbers that don't have primes because if we're looking for odds, we don't want to run into primes, right? Because you can't ever divide by 2. So we like the odds without primes. 6k plus 0. Even numbers, but they'll never be you can't divide by 2 and get anything. So these are even numbers that'll never have a power of 2. Right? And so then we know that there's the 6k plus 2 and plus 4. These are even numbers that can contain a power of 2. So you're looking at ones that'll set of like 1 and 5 that's prime, and this one here, the 2 and 4, that's even. So what we need is something that will work with 6k plus 2, 3, and 4 in order to try and find a way to, we need odds that are of the form 6k plus 3 so that we can get evens that are of the form 6k plus 2 and 6k plus 4. Right? So we need to, so that way when we get to an even, we know that it will contain a power of 2. At least it'll have the possibility. We don't want to look at ones that don't. And then when we get to an odd number, it'll never have a prime number, right? So we know we'll always have composites. So any odd number is a composite so that we can easily switch back and forth and we don't run into any snags of not being able to continue to have numbers to work with. Right? We're going to iterate, so we know that we don't want primes. We don't want a prime number that can't be anything else. It's just itself. We need stuff to work with. We need to be able to break them apart and put them back together. Right? They say, if you don't understand why that is, I don't know a better way to put it into words, so please bear with me. So down here, we'll make this another way down here where we're talking about like doing what. So here's the ones we need. The 6k plus 2, 6k plus 3, and 6k plus 4. These have the break down to a couple of different ways. This one's 2 times 3k plus 1. This is 2 times 3k plus 2, right? Yay. 6k plus 3 is 3 times 2k plus 1. Well, 2k plus 1 is also an odd number, right? We know that's always an odd number. It maintains parity. So that's 3 times an odd number. Well, that makes this 3 times an odd number minus 1. And this one, 3 times an odd number plus 1, right? We know that that's what that is. So this is one more than it, this is one less of it. Now, if we want to try and do this to an odd number, if we're working on an odd number, what do we need to do? We need to change it to one of these forms. So if we do 3 times an odd number minus 1, right, and we multiply that out, we get 6k plus 2. Now, if we try and divide that by 2, right, we know that's going to make an even number. 3 times an odd number minus 1 makes an even number that can contain a power of 2. Right? So with respect to the original k you used to make your odd, that makes 6k plus 2. We can divide that by 2. Well, that gets us to this number. When k is even, this works, right? You maintain parity, that makes it an odd. That can also work. When k is odd, this isn't true. K is odd, you have a problem. Right? When k is even, this is true, right? So when k is even, this gives you an odd number. Well, when k is even, that's fine, but when k is odd, we get an even number, right? But you get a pretty significant limit. What you get is something of the form of 6k. Well, we know that that's never going to have a power of 2, right? Anything that's also divisible by 3 is never going to have. This is actually going to mean that this is always going to be a power of 6. Blah, blah, blah. We get something that's of the form 6k plus 0. So that one isn't going to work. The 3n minus 1. 3n plus 1, however. 3 times 2k plus 1 plus 1, the 6k plus 4 with respect to the original k. Where equals that? Well, that actually, so when k is even, so is this number. So you'll still always be divided by 2, right? You'll never have to worry about this. As long as k is even, so will this. You'll always be able to divide by 2 until you get to an odd. Right? You'll eventually get to an odd. That's of a lower number. That's a different one. That's a different x, so to speak. Right? You'll always be able to continue dividing by 2 as long as k is even, because it maintains parity. 3 times an even number is even, plus 2 is another even number. When k is odd, it maintains parity as well. Not only does it maintain parity, right? You get this 2x minus 1. You go back, that's a different odd, right? 3 times the original k, which would be an odd, makes this odd number, which can also be written as 3k plus 1 is 2x. Well, 3k plus 1, this x is going to be even, right? This is going to be an odd number, so 1 away from it, 1 away from the odd is going to be an even. That even number that is going to make up this odd is going to be from this group, the 6k plus 2 with respect to the original k. And you're going to get to another one and keep running through. So whenever k is odd, this applies. And you'll switch from 4 to 2. You'll switch from this one to this one, right? Which is exactly what you want to do. You'll always have an odd, right? This is always an odd right here if k is odd. Or this is always odd, sorry, n is always odd. So when this is odd, 3 times an odd, you'll always get one of these. And 1, you'll get one of these. If you divide by 2, right, anytime k is even, you can keep going until you get to something less. Shouldn't say that because, like, well, yeah, you just do. You'll get to a lower number, right? You'll get to a lower odd. And any odd you get, the number you're basing off the next one, this k, which would be x for the next iteration. Well, not only is it going to be, right, So 3k plus 1 equals, or 3k equals an odd. So this is an odd. So this is an odd. This is going to be an even. And this even number that it comes from, that you now apply all this to, is from this. It's now this k is an even number, not an odd. It switches it. So if you've got an odd that can go, you'll always get even, you'll always get a reduction. It not only goes down, this is the only one that will work out of every possible combination of positive integers, including the only other one that would include 2 is here. We can't use this as a starting point. If you want to use the negative versions with the 2k minus 1 and the 6k minus, this all flips and the 3n minus 1 works. Anyway, that's my, I don't know what you call it, reduction, elimination. There's no other form of positive integer that will do what we're asking. In fact, by using this, it's the only one that will always ensure you have an odd that's a composite and never going to run into, right, the 3 times the odd, never going to run into a prime, so you never have to worry about this being a prime number or anything like that. And it switches between the 2 evens. You're getting the possibility, right, of it being another one. You switch parity. If this is odd, this is even, and you'll get at least a couple more. So yeah, you get to roll through this parity. It keeps rolling down. It guarantees a rolling downhill. But more importantly, there is no other form that allows the possibility for it for all k. Anyway, that's my quick proof. I'm going to post it. I'm going to have other people try to do it. I did that in really terrible language, and I know it is not formal, but there's literally no other possibility out of all the possible integers, especially when you group them this way. I love this particular little coprime feature for that. No primes to get in the way, and you'll always get odds that are of some form or family of both of these that contain powers of 2. I mean, basically, this x is going to get up to here, and if it's even, we'll just keep going down until it gets to an odd. So anytime you reach an odd, you know it'll be of the family that this works with. And anytime this is an even, it'll produce an even or a power of 2. So it'll always go down to some other composite below. Some other k that would be another composite that's going to be a composite of, well, that. An odd, 2x minus 1, right? A composite k that's equal to an odd. It maintains parity, so. Anyway, that's mine through basis. That's my elimination through algebra, coprime, and trying to create something and show that there's really no other way. Any other method would run into problems where you don't find a power of 2, you never have a composite odd, or you have the chance of never having a composite odd. And if you use these forms, this will never have a prime, and these will always be even, and they're the only ones that contain powers of 2. So you make sure you always cycle through. That's the most robust way, and showing it like this, as long as you're using positive, this one won't work. This one is the only one left. And there is no other form positive integers can take in this structure or in this way to show it. So it's the only one that does. Not only that, by nature it does. Anyway, that's my proof on that. I'm sure there's a million people who have something else, but I can't find this approach anywhere in the literature. So I'm going with it. Anyway, thanks for listening.